Good morning. Sorry, I had to restart my laptop. Now you can both see me and definitely hear me. The last one is more essential than the first. I hope you received the exercise on email in addition to a copy of the presentation of lecture 4 so that you guys could have a peek either in advance at the same time as I'm presenting or after for that matter. Also, as before, I will be recording unless somebody send a note or let me know that it is not okay. I will record this session too. Let me now like this. Are you able to see my presentation now?
Yes, we can see.
Good. Thank you so much.
Yep. Likely to zoom it a bit. I have no problem.
This one is zoomed as much as I can do it, I'm afraid. Today
it's okay. It's okay.
I did what I could in advance. Yeah. All right. I hope you received the exercise as said, and if you have any questions, let me know. I will not have any special call it session to talk through the exercise unless you guys raise any questions. There's a number of people following this class, and since it's recorded, I guess they don't show up for the lectures as per se. So they will probably be listening in on this recording, and they will have to know that if they have any questions and they want to submit their exercise, you have to contact me on the given email address in that message I sent to you guys. All right, let's just jump through it unless there are any questions so far. The exercise, yes, and what I've done, I have added a topic. As we talked about early in the casing design portion of this class, is that we have been running some, call it lab exercise. We've been running Landmark, Drilling Engineers Suite, doing analysis, and for simplifications, we do only the simple variety, not the Velcat HPHT version. We do stress check. And that is I call that for myself at least, the light version of casing design. It's quite straightforward. If you have some guidance of how to do it, it's just fill in the blanks and off you go. Of course, what we do in this class is to prepare you guys so that you know how to trust and how to feel confident about the results that you're getting. And we started last lecture with building that confidence, and we will continue in this lecture. I hope to give you this call it online version of the lab exercise that we did before. What I can do is do the exercise while you guys are following. What we can do, you can sit at NTNU on one of those laptops. I can give you the input unless it's already there on the laptop itself. Normally they should be there, and you can click and follow the steps that we're doing in stress check there to see how it works for yourself. What we talked about last lecture, quick recap, we talked about and introduced load cases and showed that there are two types. We did a little bit on triaxial analysis, and section design pressure was quickly introduced. Not very advanced calculations, just knowing what it is. The actual forces, acting forces, we have two types of load cases. There are drilling loads, as we discussed through more in detail last lecture, shown here. And we talked about the load cases for production loads and saying that these are the most severe ones and very often the ones that sets the design of the casing, meaning how thick the walls of the casing needs to be and its yield strength. We went into detail in one of the cases that are typically determining the specific of what I just said, which yield and wall thickness you need in order to have a life cycle design, and that's the tubing leak. And for the tubing leak, we also have specifics for the production casing as discussed last lecture. The section design pressure is very often coming from a load case in drilling design that we call displacement to gas. And we see here a cutout screen dump from what we used to have when we had a full class at NTNU in the autumn. It was called TPG4242. We did a full call it class where the students were doing engineering as what we are doing it in the industry. We had a set of input just as what you will get as a drilling engineer from the subsurface team, and then you have to make a well path, do the casing design, you have to do the casing wear, and you have to do the tubing design, all of which works just as in the industry. And basically we are using a real well. Everything is from a well that was drilled some years ago, and you will see how the drilling engineer solved the case, and you're making a drilling program to compare your drilling program, different groups working together. That's what we did. And we also had, like you see here, a set of governing documentation which can be made available to you should you desire it. It is like call it a principal copy of what you will be facing working for Shell, BP, Exxon, Equinor, any of the big oil companies that are out there. They would have a set of governing documentation like this, and you will have to do design in that regard. We cut out a portion of this governing documentation to show you how it actually influences how you do the casing design and your answers. Why you cannot just take what you think is the highest pressure, but there are certain regulations guiding you how to put your answers correct. Like for this case, it is adding kill margin. And we also talked about how some operators, they would also put a certain minimum overpull as your as your call it margin as you are running casing or drilling for that matter a section. We're jumping into today's topic, continuing on casing design basics, acting forces, and now we're going to look at the calculations behind these so-called load cases, because load cases, they comprises a combination of many forces at the same time. We will now look into more or less all these different single forces, and you will understand why we have a software that sets this up as a load case. Otherwise, there will be a whole lot of individual stresses that we need to put together, and we will have to see which ones are working against and which ones are working for in a supportive perspective for the casing. Let's start with the actual stresses, those who do either direct the tension or compression. We have the gravity and the component working parallel to the casing in its well path. We will be looking into thermal expansion. We have what is called ballooning effects that typically gives us external or they come from external or internal pressure. They always tend to give us tension. We have bending. It comes from putting pipes through a curvature. And then what is called buoyancy. If you put a piece of any item inside a liquid, there will be a difference from air, and also like an immediate effect if you are introducing a pressure wave into your well, like slugging, for example. That would be like a shock. Joukowski equation rules shock going through a system like that. When you're pressuring out, say, a plug in the well, that you're cycling out a plug, and then suddenly the pressure is released, you will have like a water hammer effect. Moving on to what we call bending. Bending is a very localized effect. You cannot take the stress from bending and add it further up to the well and the picture of stress. We see up to the right in this presentation a blue line. It is straight all the way to its bottom. However, where the curvature is, we see a red line and the blue dotted line in effect following it. What we can read from this S, red S, is that actually the curvature is also an S. It's an S-shaped well path. Up to the left, or more in the center in the blue square, we see how it works. We see the center line will actually be not affected by the curve, whereas the outer part of the pipe will see tension, as indicated by the red arrows. And then in green, we'll see that the inner part of the curvature will see compression. And that is what is reflected to the right. We see that there is an added stress to the pipe, so that the tension is increased in the first portion, going down to where the curvature of the well changes, and you go from added tension over to added compression. So that will be in effect what is the worst case, because again, like said in previous class, we always do worst case situations in our, call it, load cases or situation analysis. The formula is not very advanced. The stress that is added has these parameters. I'm not going to go into detail of those. You can see those listed there below. You add this localized in your analysis if you are doing a hand calculation. Otherwise, these things are built into your casing design software for each load case, and that's what typically we will see if there's time and possibilities to do a stress check analysis of a section. You'll see that we are only doing load cases, and all these individual calculations, they are not really there for you to look at. But of course, on your exam, this is what you will be facing, just as in your exercise just shared. Buoyancy. Buoyancy is actually a very, very complicated calculation. But for our case, what we will do is look at this simplified version that I am very sure that you guys have seen before. Again, very simple equation, and this is how it is for a straight pipe. It gets complicated when you start to think about crossovers and looking at that, and also there are other ways of calculating this, and there is something called fictitious forces. I just want to mention it. It will definitely not be part of the curriculum in this class, but you as drilling engineers, if you're going into these matters in your thesis, for example, it is nice to have a look at or at least know about what that is, and knowing that the brain power, the academia in drilling engineering, they have been discussing fictitious forces since many decades, and many people, they still do not fully understand what that is and use it correctly. So discussions are going, and when it comes to what we do, this simplified version is absolutely correct. It doesn't change anything for us in this class. And as said, it is built into our casing design calculations, fortunately. Simplified axial stress. Everyone has seen those before when they study this class. Very simple equation. But as said, many components working on the pipes, adding stress, and this is just a portion of it, the weight-based part of the part of the stress. Moving on to pressures. There are many factors that actually goes into the change of densities. We briefly touched upon it in last session, where we discussed what is to be supportive forces in the annuli. Annually here marked in blue, what is going on. We do again a worst case scenario. If the full mud weight as installed is the worst case, meaning like a collapse consideration, then we use the full mud weight. If it's a burst situation, we think about the mud as degraded. Normally, we can say that in casing design, the typical rule of thumb is 1 month. After 1 month, we say that the mud has fully fallen apart. Typically, what takes place in situations like that is what you will see when you are doing P&A, is that much of the weight material has fallen out of the liquid. It is like a sand plug at the bottom, and the fluid itself has returned to something like 103 SGs, like seawater or formation fluid, any density that you'll find in your formation fluid on the exposed formations, like what you see in the annulus marked in blue on this drawing. You see that the cement is not going all the way up to the shoe, meaning that the formations that are exposed there in the gap between those casings, you would typically use that pore pressure in that segment and say this is the minimum. It all depends on the philosophy of the one you are working for, and you'll find these things in the governing documentation. And should you not, it's a very relevant question that you should put on to your technical supervisor, your technical boss, to put it like that. This is what we do as drilling engineers, and I have to lecture that every year. We put up all the things that we see in our analysis, and we discuss all these presumptions with our, call it superiors, immediate superiors, and say this is what I've done, this is the foundation of my analysis, these are the options that I see. Please let me know if you want it otherwise. Yeah. So any formation fluids on the outside in the annuli would be subjected to changes, whereas also, of course, what you are producing is changing also over the life cycle of the well. There are many things that can take place. We could have a gas breakthrough, a water breakthrough, or in some cases, the well could be changed either to a gas injector or a water injector, or what is called a water alternating gas injector. You could also have breakthroughs of these different fluids. So going from the initial plan, you may actually have something entirely different at the end of the life cycle of the well that you need to account for in your design analysis. What is very important to consider, and probably one of the extreme cases, is the temperature changes that takes place. I think that I am very much correct when I say that the temperature changes will be the most advanced calculations in casing design and getting the stress correct from the temperature change. Going at that last step from the temperature to the stress is not that difficult, but getting the temperature right, simulating the temperature is where the nut is. That nut, cracking that nut is the difficult part. We'll look into it a little bit later. Yeah. Changes in formation, say that you add new perforations with different pressure regimes. Sometimes what we do is perforate the well where it absolutely was not initially planned and might not have been considered at all in the original casing design. So that is something to mark very well behind, somewhere in your professional ledger, that please consider if you're perforating, say, and doing a through tubing drilling situation and so on, that the original casing tubing design needs to be revisited and upgraded to accommodate new pressure regimes and uses of the well. That error has been done before in the industry, and it's likely that failures will come unless we are very thorough about these things. Surface applied pressures, say you're doing a fracturing, say that you are initiating some new use of a well by perforating in an old well, shale formations, and fracturing them. That would be a typical example of just what was discussed. And the water hammer, the shocks that we talked about, perforating could be one of these shocks taking place in the well. Sometimes these are quite significant. Ballooning always seems to give an added tension in the pipe that it is acting on, regardless if what you're doing is pressuring up internally or externally. I hope and think that the drawing on this slide is actually visualizing the situation and the cause of the origin of the ballooning, so that I don't need to explain that too much. Internal pressure will widen the pipe, as seen to the left in the drawing, and that makes it shorter. It wants to retract. Knowing that the pipe itself is actually fixed by cement in the bottom and locked in the casing hanger on top, the ballooning then will definitely add tension. Now, what I said about tension added would not be true for a piece of pipe that is fixed in both ends. If you are pressuring in the annulus, then the extension may actually result in a relaxation of the already added tension. It all depends on the situation. The equation for calculating the ballooning, we see a formula here. There is also the Laplace formula. We in this class present only this equation here. You can check out other formulas for ballooning for yourself. Moving on to temperature's effects. The source of the temperature, the stress from temperature, we can see that in the picture graphically, as the temperature in the bottom of the well, the reservoir, typically when you are producing, it will follow a path like the red stapled almost vertical line, whereas the geothermal gradient is marked in black. Typically what takes place is that, say, I can take an example from one of our wells that we have drilled. In a reservoir at 4,000 meters deep at approximately 150 degrees Celsius, even at a well that is sitting subsea in a temperature environment of 4 degrees, quite good cooling effect from the sea. The producing fluid holds around 100 degrees. So at the top of the well, sitting in seawater, the flowing temperature of the liquid at the top is 100 degrees. It cools down some, just shy of 50 degrees Celsius. So all that energy, all those 50 degrees is what goes on, what goes out and is absorbed by the infrastructure of the well. All the different casings get heated up. And again, I have to remind you guys what we talked about the last time. Initial condition. We will see exactly what that means, and I think that's also in your exercise so that you guys can see and hand calculate for yourself what that difference actually means. Here it is. There are in reality three main categories of call it energy transfer from temperature effects. Conduction, meaning that heat from the annulus actually is going straight through the physics of the material in the well. And then we have convection, which is divided onto two groups, diffusion and forced convection, or advection as it is called. We see it graphically where it would take place in the drawing down to the left. Typically diffusion is when you heat up your annulus, and that warmer liquid would ascend while it changes place with the colder liquid at the bottom. So that is one, call it indirect or resulting effect of the temperature that is influencing the infrastructure in the well. Forced convection, that is when the reservoir fluid is actually going up, and that is of course coming from the pressure differences. Finally, we have what is an electromagnetic wave or radiation that takes place, and it's not depending on any material at all. So we have more or less 4 calculations that we need to do, and we need to know, and that is probably the one of the more difficult ones, knowing the heat capacity of exactly what is it that you are producing in your well. So on one side, you have to have a really good understanding of the composition of what you are producing. You need to know what is in gas phase and what is in liquid phase and the different compositions, their heat capacity. And once you know that, you can start the calculations of these 4 different listed temperature, how to say, energy transfers. Knowing what is exactly the different coefficients for the different fluids that we see physically here is work intensive. That's what it is. It's not impossible, but when it comes to losing or the formations absorbing temperature and the exact temperature in the outside at different depths is also a little bit tricky. Getting the temperature correct, we are getting better at doing that now, since for example there are these wells with very good data collection. I know that in the Norwegian sector, this Johan Sverdrup field, what they have is fiber optics that takes in the temperature for every meter in the wells, and you can start to adjust your calculations and know exactly which factors are to be used in the calculations, also for other wells. When it comes to these advanced calculations that were just discussed, we will not do them in our class. It's so specialized that it goes beyond the scope of what we do. What I think is good for you guys is to have an understanding of it. So having a theoretical question about this, the previous slide, for example, in the exam would not be unthinkable. But as in the exercise, what we are doing, we are saying that there is a certain delta T, changing temperature from initial conditions, and then you guys will calculate the resulting stress. And that is as simple as we see in this equation. The resulting stress is basically from a coefficient of thermal expansion and the Young's modulus. So it's not at all complicated to get the stress as long as you know the temperature. Yeah. And with that, I think we have arrived at our break. Thank you guys for listening, and I have to apologize again that my start was absolutely not perfect this time, meaning you couldn't see me or hear me. I think we have a question.
Yeah,
yes.
I just want to request something regarding the exercise. I don't know if it is possible to extend it by some days or by a week, because we have other courses with a series of exercises. It's just a request.
No problemo. We are adding 1 week, if that is enough. We'll then go from the 6th until what would it be? The 13th, is it? The subsequent, yes, Thursday 13th. I will send out a message saying that we delay it until the 13th. Would that solve the matter?
Yes.
All right. Thank you, guys. See you after the break.